What is a particle ratio? It allows you to convert between particles of A and particles of B. And you find it by writing the formula. So it's going to be different every time. So it's not like I can write down the particle ratio. There is a different particle ratio for every compound. Okay? So for example, if we have dinitrogen tetroxide, that's 2 nitrogens and 4 oxygens, N2O4, and we have a lovely little picture of our N2O4, we can write a ratio of N atoms to N2O4 molecules. There are 2 N atoms for every 1 N2O4 molecule. Look, there they are, 1, 2. Yeah? Now, what we're going to do is we're just going to scale this up. Ratios scale up. So the ratio is going to remain the same. So if I give you 1 pair, how many is a pair? 2. So I'm giving you 2 molecules, that's 1 pair of N2O4 molecules. How many pairs of nitrogen atoms do we have? We have 2 pairs. Here's 1 pair here. Here's another pair here. So the ratio is the same. We have 2 pairs of N atoms for every 1 pair of N2O4 molecules. 2 to 1, 2 to 1. Now, what if we had even more? What if we had a dozen? Yeah? Look, here we go. Here's a dozen. 12 molecules. Okay? And then if we count up the N atoms in these 12 molecules, 1 dozen N2O4s, we can count up, we can say I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So 12 in that one row and then another 12 in the next row gives us 24 N atoms, which is 2 dozen N atoms. And we have 12 N2O4 molecules, which is 1 dozen N2O4. So the ratio is once again exactly the same. We have a 2 to 1 ratio. There are 2 dozen N atoms for 1 dozen N2O4 molecules. Now, what if we scale up to an even bigger number? What's a really big number that we know? 6.02 times 10 to the 23. We know a mole. Yes? The ratio for a mole, there's going to be 2 moles of N atoms for every 1 mole of N2O4 molecules. Yeah? And it just gets bigger, but it's always 2 to 1, 2 to 1, 2 to 1, 2 to 1. Okay? You can do this with atoms. If we have 2 N atoms in this molecule, then we have 4 O atoms. So we have 2 N atoms for every 4 O atoms. But that scales up. We have 2 pairs of N atoms for 4 pairs of O atoms. And we can do the same thing for a dozen. 2 dozen N atoms for every 4 dozen O atoms. And then we can scale that up even further. So we have 2 moles of N atoms per 4 moles of O atoms. So now what we have is we have this mole to mole ratio, and that is what we call the, instead of the particle ratio, it's called the mole ratio, because you have a relationship between the moles of A and the moles of B. Okay? Moles of A to moles of B. And it is the same numbers as the particle ratio. So if we have C2Cl6, the mole ratio for moles of carbon to moles of chloride is just 2 to 6. We get the numbers from the formula. If we want the moles of carbon to the moles of C2Cl6, there are 2 moles of carbon in every one of the entire thing, 1 mole of the entire thing. Easy enough? Basically, this just allows you a shortcut, all right? Because if I said, if I gave you 17 moles of carbon atoms, how many moles of C2Cl6 could you make? You could convert moles of carbon atoms into the number of carbon atoms and then use the particle ratio to go from the number of carbon atoms to the number of molecules. And then you could go from the number of molecules to the number of moles. Or you could just go from moles of this to moles of that in one step. Okay? If you never learn this ratio, it's not the end of the world. You can do a 3-step conversion, but this saves you a lot of time and energy. Yes? Okay. So I'm not going to, this is homework. We're not going to dilly-dally on that. And we are going to go then to page 34, I think. Let's try 34, see if that's right. Yes, it is. Excellent. And we're going to hang out with Tyler for a little bit, page 34. Oh, no, not 30. Yeah, this is 34, but I have the wrong page here. Page 34. There we go. That looks better. All right. I got the subtitles on because this is an old video and the sound is not particularly good. All right.
In this video, we're going to look at how we can use moles to count the number of atoms we have in something. So, for example, here I've got a container with a bunch of chunks of carbon in it. I want to know, how many carbon atoms do I have here? We'll learn how to figure that out here. So, just a quick review of moles. A mole is kind of like a dozen, except there are 12 things in a dozen, and there are 602 hexillion things in a mole, and we often abbreviate this number in scientific notation as 6.02 times 10 to the 23rd. Now, let's take a look.
All right, so just take a moment and fill in 602 hexillion
Look at a mole.
And 6.02 times 10 to the 23. While he brings over the little container of sulfur atoms.
Right here, I have a mole of sulfur atoms, which is just about 602 hexillion sulfur atoms.
I want you to think about that number, how huge that number is, and how small that little container is. That gives you an idea of how teeny tiny, itsy bitsy, very, 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 very small atoms are. They're so small that 602 hexillion of them, sulfur atoms, take up that much space.
Now, this is pretty crazy because it's such a giant number of sulfur atoms. Here's my question. How do I know that there are 602 hexillion sulfur atoms here, right? I couldn't count them out for two reasons. One, atoms are way too tiny, right? We can't even see them with a very powerful microscope. So there's no way that I could have seen the atoms and counted them out. Second of all, even if I could count out the sulfur atoms, there are so many things in a mole that it would take 20 quadrillion years to count from 0 up to a mole. So even if I could see these atoms, there's no way I could count them out. Yet I'm pretty confident that there are pretty close to 602 hexillion sulfur atoms in here. How do I know that? Well, we're going to learn more about this, but it turns out that I can figure out how much a mole, 602 hexillion sulfur atoms, weigh, and then I can put this thing on a scale and weigh out that number of sulfur atoms. Let's talk a little bit more about this so it makes a little bit more sense. Okay, so here's an analogy. Let's say that I work at a candy factory, and when someone places an order, it's my job to count out all the pieces of candy that they ordered. Okay? One day, a giant rush job comes in for 10,000 jelly beans, and the person who placed this order wants exactly 10,000 jelly beans. What a pain this is going to be, right? I gotta 1, 2, 3, count out 10,000 jelly beans. This is going to take all day. What could make my life a whole lot easier?
Any ideas? Holes? Moles. Well, maybe, but we don't need 602 hexillion of them. Yeah? Weighing it? Yeah, absolutely. Okay? And this is going to tie in very nice with the idea of the mole because we weigh moles. We count moles out by weighing them because it's too, like he said, 1 atom, 2 atom, you're here, a quadrillion years later, and you still haven't finished counting.
Well, one thing that would be really awesome is if I knew how much 10,000 jelly beans weighs, right? So what if I figured out that 10,000 jelly beans weigh 27,130 grams? That would be really awesome because then all I would have to do is put a big bag on a scale and just shovel the jelly beans in until I got 27,130 grams of them. So in other words, instead of having to count, if I know how much 10,000 jelly beans weigh, all I gotta do is weigh out that amount. We can do the exact same thing here with moles. I told you there's about 602 hexillion sulfur atoms here. Of course I didn't count that out. That's because I know that 602 hexillion sulfur atoms, a mole of sulfur atoms, weighs just about 32.07 grams.
Can you think where he might have gotten that number from? You could find that number. It is on the periodic table. Yeah. If you look, grab your periodic table, you'll want it. Okay, so make sure you've got a periodic table kicking around and go find 32. Yours is going to say 32.1, not 32.07. What's wrong? Did you lose your periodic table? Oh, you're good. Okay. All right. I don't know what you said, but it's okay. Probably doesn't matter, does it? What? Okay. Can you find that 32.1 on there? What is it? That 32.1 is the atomic mass. So the mass of, and when we say atomic mass, we mean the mass of how many atoms? Literally, it says atomic mass. So it would be the mass of how many atoms? It's an average, but it would be the average mass of 27 atoms, 13 atoms, 1 atom, because it is the atomic mass. Yeah? Yeah, so you take all the isotopes and you average them out and you get an answer in AMU. So if you have hydrogen, okay, and maybe I'll actually write this on the projector this time so it comes through in the video. If we have 1 hydrogen atom, it has a mass of 1 atomic mass unit. Yeah? But if I give you 6.02 times 10 to the 23 H atoms, that has a mass of 1 gram. So literally, they picked the number 602 times 10 to the 23, because it allows us to scale from AMU to grams and keep the number the same. If you picked a different number, if you picked 1.2 times 10 to the 24, then the mass of 1 mole of hydrogen would be 2 grams. And that's kind of useless because you would like it to be the same number. Yes? Where did they get 6.02 times 10 to the 23? Well, they said, how many hydrogen atoms does it take to weigh 1 gram? And that's 6.02 times 10 to the 23. Yeah? They actually did it with carbon. What they did is they said, okay, if I have 1 carbon atom, that has a mass of 12 AMU. Okay? 1 carbon atom. Now, how many carbon atoms does it take to get to 12 grams? Well, that's going to be 6.02 times 10 to the 23 of them, carbon atoms. And that's how they decided on the number 6.02 times 10 to the 23. It's just, that's the number that gets us to 12 grams, so that this number will be the same even though we're changing the unit. Huh? I missed a 2. Oh, 23. Thank you. Okay, we're good. And what that means is that if I had 1 hydrogen atom, the mass in grams would actually be 1 over 6.02 times 10 to the 23. It would be 1/602 hexillionth of a gram would be the mass of 1 hydrogen atom. Now, if that whole scaling thing makes sense to you, that's fantastic. If it doesn't, it's not the end of the world at this point. Okay, you just need to know what atomic mass is, and you need to know what molar mass is. All right, and you'll play with these numbers a lot more, and gradually over time, you will feel more comfortable with them if you don't already. Okay, so don't worry if this seems like, what is happening over here? What she got? I don't understand this fraction. It's okay if you don't understand that fraction at this point. If you do, that's just a bonus. All right, let's go back to Tyler.
So all I got to do is put this container on a scale, weigh out 32.07 grams, and I know I have just about 600.
Sorry? Oh, it's not related to this. Can we wait until we're done then?
And 2 hexillion of them. So how did I know that a mole of sulfur atoms weighed 32.07 grams? Well, all you got to do is look at the periodic table. If I look sulfur up on the periodic table, I've got the element name and the abbreviation and stuff, and then I got this number down here. This is what we call the molar mass. And this number down here tells us how much 1 mole of this element weighs in grams.
Okay, so you can fill that in. That number down at the bottom, which we have called atomic mass, is also called the molar mass. And it's how much 1 mole, 6.02 times 10 to the 23 atoms, weighs in grams. How much 1 mole weighs in grams? We're not there yet. Don't worry about carbon yet.
So 32.07 is how much 1 mole, 602 hexillion sulfur atoms weighs. Now, let's go back to the candy factory. Imagine that I get all kinds of orders for all sorts of different candies. I can figure out what 10,000 of many different types of candies weigh. So, for example, maybe I have to do M&Ms one day, and I can find out that 10,000 M&Ms weigh 8,770 grams. They weigh less because one M&M is much lighter than one jelly bean, so 10,000 of them are going to weigh less. On the other hand, a candy like one of these chocolate malted balls, very delicious, are a bunch heavier than the jelly beans, so 10,000 malted balls are going to weigh a bunch more, 154,600 grams. So it's the same way with atoms.
Okay, so basically he's doing everything in 10,000s, but we're with the atoms going to do them in 602 hexillions, in moles.
Some are lighter and some are heavier. So carbon, for example, is a little bit lighter than sulfur. And 602 hexillion carbon atoms only weigh about 12.01 grams.
So you can fill in that number where it says carbon, 6.02 times 10 to the 23 carbon atoms weigh 12.01 grams.
Because carbon atoms are just lighter than sulfur atoms. On the other hand, something like zinc atoms are heavier than sulfur atoms. So 602 hexillion zinc atoms, a mole of zinc atoms, weigh 65.38 grams.
So you can fill that in, 6.02 times 10 to the 23 zinc atoms weigh more. They weigh 65.38 grams.
And just as I did with sulfur, I know how much the carbon and zinc moles weigh because I can look up the atoms on the periodic table. So here we got carbon, 12.01 is...
And you can fill that in there, 12.01.
Its molar mass, that's how much 1 mole weighs. And zinc, look that up on the periodic table, 65...
Yes. We're going to use our periodic table. So our values from our periodic table are always going to have 1 decimal place, okay? And even when we get into compounds and we start adding up the molar masses, remember with addition, we always go to our first uncertain digit. And all of these digits, the uncertain digit is that 1 decimal place. So molar mass in this course will always be to 1 decimal place. Good question.
5.38, and that tells me how much 1 mole of zinc, 602 hexillion zinc atoms weigh. So, if I want 602 hexillion, 1 mole, of any kind of atom, all I gotta do is look on the periodic table and find out how much a mole of that atom weighs. And then I don't have to count any atoms. All I have to do is just weigh out this amount on a scale. This is just like me being lazy in the candy factory. I don't want to have to count out these jelly beans or M&Ms, so I can just weigh them instead. I can do all my counting by weighing, and that's what I do with these atoms. I count by weighing out their molar masses. So, now that we know how to figure out how much a mole of atoms weighs, let's go back to that original question that I asked at the beginning of the video. I have here in this container a whole bunch of carbon. I want to know how many atoms of carbon are in here. Let's see how we'll answer this. Okay.
Okay, next page. I don't think you have to flip. I've got a different version of this book. Okay. 1 mole of carbon is 602 hexillion. Atoms is 6.02 times 10 to the 23 atoms. And that weighs 12.01 grams.
Okay, so how many atoms of carbon do I have in this container? Well, let's think about moles of carbon. I look up carbon on the periodic table and I find out that 1 mole weighs 12.01 grams. And I also know that in that 1 mole, there are 602 hexillion atoms. So the first thing I want to know is how many moles of carbon do I have here? In order to figure that out, we can do some weighing, all right? I know that 1 mole weighs 12.01 grams, so let's weigh this and figure out how many total moles we have in here. I put this on the scale and find out that there are 31.87 grams of carbon atoms in here.
So, is there more than a mole there, or is there less than a mole there? more, right? Because 1 mole is 12 grams-ish, and this is 31 grams-ish. So we have more than a mole. Almost 3 times as much, not quite 3 times as much.
Now that's more than a mole. If we had 12.01 grams of carbon, we'd have 1 mole, but we have more than that. So let's figure out how many total moles we have. We'll do that by taking 31.87 grams, the total mass of carbon atoms here, and divide that by 12.01 grams, which is how much 1 mole weighs. And when we do that, we get 2.654 moles. So that is how many moles of carbon I have in here.
Okay, so you can fill that in. We're going to go over this again later and do it via conversion factors, just because I'm a conversion factor crazy person. Can't do without the conversion factors.
Okay, we'll take this number, hold on to it, because it's going to be important for what we do next. Okay, so that is
Guys,
how many
did you get enough time to copy those down? Yeah.
moles of carbon I have in here. Okay, we'll take this number, hold on to it, because it's going to be important for what we do next. Okay, so how many atoms of carbon do I have in here? Well, we know that in each mole there are 602 hexillion atoms, but here I've got 2.654 moles. Okay, this isn't too hard though, because all I got to do is multiply 2.654 by the number of atoms that are in 1 mole. So I can do 2.654 moles times 602 hexillion atoms. Now, this is kind of a pain because I got all these zeros, so I'm going to rewrite this using the shortened version of this in scientific notation. Let me just move this up, and instead I'm going to multiply this by 6.02 times 10 to the 23rd, which is usually the version of 602 hexillion that we want to use when we're doing math. When I do this, I can just plug it into a calculator. I'm going to get 1.60 times 10 to the 24th carbon atoms. Oh, I forgot the R. Carbon atoms. There we go. And now, again, sometimes when you see things in scientific notation, it can be a little bit scary, a little bit tricky. So let's put this out of scientific notation. And this is the number of carbon atoms that we have when we put all those zeros in.
Quite frankly, I find that number more scary than scientific notation, because that's a lot of zeros. Yeah? It looks less scary when it's without it, but it is a whole crap ton of atoms.
A whole bunch. 1 heptrillion, 600 hexillion carbon atoms. So that is how we can use moles to figure out the number of atoms we have in something. We can figure out how many moles we have by weighing it, and then once we know how many moles we have, all we've got to do is multiply that by the number of things that are in a mole, and we get our final answer.
Okay, and we're going to leave it there. I think that is the end of the video anyway. And we are going to go here. Please wake up. Okay, there we go. Okay, it's kind of waking up. Here we go. All right. So we got to here, and we had this number here. We had 31.87 grams divided by 12.01 grams, and we got 2.654 moles. Now, if you know me, I'm not really happy that I had grams and I ended up with moles. My units are not really looking so good there. So what we're going to do is we are going to use the molar mass as a conversion factor. Now, first of all, what is molar mass? Tell your partner, what is molar mass? You're absolutely right. It's how much 1 mole weighs. It is the mass of 1 mole. Okay, so it's the mass of 1 mole. So then what would the unit of molar mass be? No, that's atomic mass units. And remember, an AMU is actually 1/602 hexillionth of a gram. Okay? What is the unit of molar mass? Yeah. That's part of it. Let's take a look. It is the mass of 1 mole. So it is literally grams per mole. And rather than writing it as grams per mole like that, we're not going to do that because then it does not look like a conversion factor, and we would like it to look like a conversion factor. Okay, now do I have enough room to do this? Maybe, maybe not. We'll find out. So if we say to ourselves, how many moles do we have if we're starting with 31.87 grams of carbon? And doing it the unit conversion way, we end up with grams of carbon. We need to put grams of carbon on the bottom to cancel out. And we want to find moles. So moles of carbon have to be on the top. And do we know a conversion factor that relates grams and moles? Oh, look at this. We have a conversion factor that relates grams and moles. It is the molar mass. Allows us to go between grams and moles. So if you're ever like, oh, I got grams, I got moles, what can I use to convert? You use the molar mass. Where do we find the molar mass? On the periodic table. So we say, okay, I know that there are 12.01 grams for every 1 mole. And remember, the 1 goes with the mole, the 1 goes with the mole, the 1 goes with the mole, right? Same thing here. The 1 is going with the mole. We do our calculation, and oh my gosh, look at this. We have 31.87 grams of carbon divided by 12.01 grams. And so the calculation is the same. We've just shown it using unit conversion. Yes? And we could do our second step where we have our 2.654 moles. Here we had 6.02 times 10 to the 23 atoms. Instead of just saying atoms, we could put that over 1 mole, because that's the ratio that Avogadro's number gives us, right? And so then our moles will cancel out and we will be left with atoms. Is good? Okay. We're going to try a few of the questions that follow this together. Okay, so let us use your periodic table to determine the mass of 1 mole of magnesium. So according to your periodic table, what is the mass of 1 mole of magnesium? 24.3 grams. Now, it didn't ask us for the molar mass, it asked us for the mass of 1 mole. I know that sounds like a weird thing, but it's okay. Now, what is the mass of nitrogen? The mass of 1 mole of nitrogen? 14.0. Don't forget the 0.0. If you leave this off, you lose 0.5. Your molar mass should always be to 1 decimal place if you're using this periodic table. If you have a periodic table with more decimal places, your answer will be to more decimal places. But grade 11, always 1 decimal place. And the unit is grams. Now, what if, do you guys know something about N2 in nature? N2 is a diatomic. Yes? Yeah, it is a diatomic. What would the molar mass of N2 be? So N is 14. What is the mass of N2? 28 grams. 0.0 grams. Yeah, all you had to do is multiply by 2 because we've got 2 atoms instead of 1 atom. Yeah? Okay. I'm going to let you do these next 2. We don't need to do those together. Let us take a look at question 3 on the next page. Let's write the molar mass of sodium. What is the molar mass of sodium? 23.0 grams per how many moles? 1 mole. All right. Let's try fluorine. What is fluorine? Molar mass of fluorine? 19. 19.0. And we need our grams. And on the bottom, we need 1 mole. Now, what if I said not fluorine? What is the molar mass of F2? That would be 38.0 grams of F2 per mole of F2. And actually, unless I say fluorine atoms, if I say fluorine is a diatomic, you would have to assume that it is diatomic and go with this one. Okay? That's the better answer. All right? Yes. Was that what you were going to ask earlier? Yes, no problem. What is the mass of 3 moles of sodium atoms? We're going to do this using conversion factors. So what is the mass? Mass is measured in grams. So we're going to say how many grams is 3.00 moles of Na atoms. Can we go from moles to grams? Do we know a conversion factor that converts moles to grams? Yes, that would be the molar mass. Okay, so we're going to say, alrighty, we're going to cancel our moles of Na atoms. And we're going to find the grams of Na. And what numbers do we put in there? 1 mole and 23.0 grams, which we got from the periodic table. Okay, and we get 3 times 23 is 69, and that's my answer. Are we done? No. 0.0 grams of Na. Okay? Okay, we're going to leave the rest of this for a moment, and we are going to go to page 40. And I know this is like really cramming everything in, but we've got a very short class today, and I want to give you some stuff to do on the weekend. Because of course I do. Now, I could probably even let you guys figure this out because you were very cleverly able to figure out that the molar mass of F2 was 2 times the molar mass of F. So all we're going to do now is we're going to put a few different atoms in there together. So we're going to start with CO2, which has 1 carbon, and it has 2 oxygen. Yeah? And so in order to find the molar mass, we're going to have 1 times the molar mass of carbon, which is 12.0. And we're going to have 2 times the molar mass of oxygen. What is the molar mass of oxygen? 16.0. All right, so that's going to give us 12.0 and 32.0. So when we add that all up, we get 44.0, and our unit is grams per mole. Did that make sense? So we just added those 2 numbers up. We got the carbon mass and we got the oxygen mass, and then we added them together. Yeah? Is good? Okay, cool. We're going to skip water because that seems too trivial. Okay? Just noting, you do have to have this 0.0. Okay? We're going to go down to calcium phosphate because that's a big fancy one. All right? And we're just going to follow along in here because we're almost out of time. So we have 3 calciums. Yeah? Which means we need to do 3 times the molar mass of calcium. So we get this from the periodic table. Okay, 40.1. And 3 times 40.1 gives us 120.3. This is where you need to be good at reading the formula and figuring out how many atoms. How many phosphorus atoms do we have in this formula? We have 2. 2 phosphorus, 2 times 31 gives us 62. How many oxygens do we have? 2 times 4 is 8 oxygen. So 8 times 16 is 128.0. We add those all together and we will get 310.3 grams per mole. And even better would be if we wrote grams of Ca3PO42 per mole. Is it irritating to have to write out that formula every time? Yes, yes it is. Do I like writing it out every time? No, because when I do it on the typewriter, God, I aged myself there. When I do it on the computer, I have to type out 310.3 grams, Ca control plus 3 bracket PO control plus 4 bracket control plus 2. Right? Because I got to do all the like subscripts and superscripts and all that stuff. Anyway, there we go. That's it. We now have 4 conversion factors. Right? We got number 1, we got the particle ratio. So for example, we might have 2 O atoms for every 1 CO2 molecule. Particle ratio. Different for every compound. Second thing we have is we have the mole ratio. And that would be like 2 moles of O atoms for every 1 mole of CO2 molecules. What do you notice about the particle ratio and the mole ratio? They're the same. Particle ratio goes from particles of A to particles B. Mole ratio goes from moles of A to moles of B. What is a third conversion factor that we have? Grams to moles, we have molar mass. So for example, 44.0 grams of CO2 per 1 mole CO2. And where do we find that from? We find that from the periodic table. And what's the last conversion factor that we know? It's actually the first one you learned. Avocado's number, except for it's not avocado, it's Avogadro. Avogadro's number. And that converts, we have 1 mole of particles is 6.02 times 10 to the 23 particles. And what we're going to start to be able to do is we're going to start to be able to chain these together next week. We started chaining yesterday when we went from particles A to particles B to moles of B. Pretty soon we're going to be able to go from grams of CO2 to moles of CO2 to number of CO2 to number of O atoms. 4 steps. Woo! But in the meantime, your homework is that. 26 to 28 is mole ratio. 35 to 36 is a little bit more on molar mass. This is calculating molar mass. This is using molar mass to do conversions. If this is too much because your weekend is very busy, do every other question. Okay? Every other question. But if you have a little bit more time, spend the time doing them all, get a little extra practice in, get feeling really comfortable with it. Manage your time as best you can, okay? Huh? I've noticed that. Anyone else's bus come in 2 minutes? No, okay.